So what we're gonna do today is to look into still on randomized algorithms, and we will look at a really useful trick called median of means trick. Okay, this is gonna be like kind of something that is powerful and used like it's gonna be useful beyond just streaming algorithm. But we see that its application in streaming algorithm, but it's just useful like in many places. So what is this trick? The trick is here. Like consider this scenario. That is, suppose that there is some number q that you want to estimate, right? Like some percentage of population that have some property, or a thing like in the last question in the exam, you have you want to estimate the probability that an assignment would satisfy the CNS formula. Like just some number that you want to know. Okay, so now suppose that, okay, this is something that we don't know. And let's say that x is just some random variables such that the expectation of x is q. Okay. When this is the case, then we call this unbiased estimator of q. Okay. So at least it's like some random variable such that it's expected to be q. It might deviate from q a lot, but at least in expectation it's q. Okay. So this is like some weak thing. Unbiased estimator is just some weak object. Okay. Now here is another object that is much stronger. Z. We said that Z is epsilon delta estimator of q. If basically with high probability, Z is basically q with like small, with a small deviation. That is q. Z is between 1 plus epsilon times q and 1 minus epsilon times q with high probability. So it's kind of Z is now like really kind of close to q with good probability. Yeah.
Does being an epsilon delta estimator imply that it's also an unbiased estimator? Or can you have a biased estimator?
It might be biased. Yeah, it might be biased, but it will not. Yeah. So yeah, this doesn't imply this. Yeah, good point. Yeah. Okay. But yeah, this is usually what we want. We want some really like a good estimator of q that is basically q with high probability. Another way to look at this is just that Z deviates from q by more than epsilon q with like a tiny probability. Okay. And what we're gonna do today is to see that there is like a really generic way to turn any biased estimator to epsilon delta estimator. Okay. And that trick is called median of means. Okay. So the idea is like to take the mean and then take the median. That's it. How? Okay. So let's do the first step, which is to take the mean. Okay. So the idea is that, okay, if we want to make any unbiased estimator to concentrate more to its expectation, then the idea that you can always do is try to make independent copies of the unbiased estimator and take the average. So let's say, so what do I mean by here? Like, let's say X is an unbiased estimator of Q. Now I make K independent copies of X, K1, K2 up to K, sorry, X1, X2 up to XK. and then take the average. That is just sum up the x and divide by k. So y is just the average of xi. So now let's try to see what is the expectation of y and variance of y. So I want to claim this. I want to claim that expectation of y is just the same as x, which is q. So y is an unbiased estimator of q. But the variance of y is reduced by a factor of k. Okay. So anyone have explanation why expectation of y should be the same, should stay the same? Yeah.
You could just do the linearity of expectation and just split it out and then divide by k on the units for the multiple of k.
Very good. David, right? Thanks, David. Right. So for expectation, we just write down the we just see that the expectation of y, which is the average of xi, is here. Then takes the linearity of expectation. So you put the expectation inside the sum. Each of these is q. So this is just the average of q k many times. So this is just This is just expectation of x. So just take the average of the same thing k times, so you get expectation of x. Okay. So now let's try to do variance. Okay. Can I ask you to try to do this on your own for like 1 or 2 minutes, just so that you have more experience of calculating this kind of thing. So I give you 1 or 2 minutes on this. Try to prove this. Anyone knows how to prove this? Scott?
So we can write variance of y as variance of 1 over k summation of xi.
Okay,
Just
I
about.
just follow what you say. Variance of 1 over k xi.
And then when you take the variance of a constant factor, it gets squared. So that's equal to 1 over k squared variance of summation of xi.
Right.
And then since we said they were independent, we know that linearity of variance holds. So you just get 1 over k squared times k variance of x, which is just 1 over k variance of x.
Good. So one sec. Just to this is because basically for any constant c you have c square variance of x, and this thing you can take the sum of the variance because xi are independent. Okay. Right. Square here. And each of these is just the variance of x. So this is right. Good. So we have that the variance of y is just like when you take k copies and take average, then the variance reduced by a factor of k. So in general, like if k, let's say, grow to infinite, then the variance of y would be 0, which mean this would mean that y is just exactly q. Right? Like it's like there's no variance. Like variance is 0. Yeah. Because the variance just asks how much you deviate from the expectation. But if the variance is 0, then it must be exactly the expectation. But okay, in general, k is not too large. K is just something that we can choose so that you reduce the variance. Okay. So now, okay. So now I can ask, like, suppose I ask how many copies of x do we need so that y become like epsilon 1/3 estimator of q. That is, we want that q deviate from, like, y deviate from q by at least epsilon q. This thing happened with probability just 1/3. Okay. I want this. How many copies do I need from x? I claim that, okay, I need this much. If we set k to be this much, then y will not deviate from q by too much. And to do this, like we can just apply Chebyshev, right? So from Chebyshev, from here, we just get that this is at most the variance of y over this deviation square. This is just Chebyshev. And the variance of y is 1 over k times the variance of x. And well, q is the expectation of x because x is unbiased estimator. So we just get this exactly. But I just choose k to be like kind of, basically I choose k to be big enough so that k cancel with everything here. And I get 1/3 here. This is nothing, just calculation when we after applying Chebyshev. Yeah.
Could we also use like Chernoff here if we wanted to?
We could use Chernoff, yes. Let's see. But why don't I use it? Let's see. Right. So because it could be the case that maybe like for Chernoff, right? What do you have for Chernoff? Chernoff, you get something like of the form where it's like epsilon square. Like if you apply Chernoff here, you're gonna get something like epsilon square and q, this thing, where q is just the mean of y. Okay. If you know that if you know that q is big, then you can use it. It would give you something nice. Sometimes q is tiny. Like sometimes q is just like 0.1, for example. So when you apply, like when q is not too big, then like this bar is not strong. Make sense? But here, like we can make this to be small, constant as much as we want, just by setting k to be big enough. Okay. Right. Okay. So that's one thing. Whatever unbiased estimator you have, make copies, take average. Then it will become like a epsilon estimator. Epsilon like a 1/3 estimator. If the number of copies is big enough compared to this thing. Okay. And now the next step is to I want to transform epsilon 1/3 estimator to epsilon delta estimator. Okay. And the idea here again is to take copies independently and take the median. Instead of average, take median. Okay. So in particular, like suppose I have y, which is like epsilon 1/3 estimator. And then I make t independent copies and set z to be the median of yi. Then I claim that z now must be really good, the probability that z is an epsilon estimator is really good. Like z is a epsilon delta estimator. So okay. So let's try to prove this. That is, I asked how many copies of y do I need to make z to be to get that z is epsilon delta estimator, which is this. I claim that the number of copies is just like something like log of 1/delta. So just logarithm of 1/delta. Okay. So here the idea is gonna be something similar to your homework. Okay. So let's try to prove this. I'm just gonna define the set of index I huge. It's just all the copy I, all the index I, such that the copy yi is too big compared to q. And I tiny is just the same. It's just that yi, this copy is too small compared to q. And the idea is we expect that the number of this guy, both I huge and I is tiny, not too many, like this set should be small. we expect that they should be small. But if the median is wrong, then some of this must be large.
Sorry, I have a question. Can you go back to before we do the medians?
Yeah.
For like when we were looking at y.
Like here?
Why can't we just make y in epsilon delta estimator? Because I feel like, if you look at k, if you just set the 3 to be some arbitrarily large value, you can get a probability that's arbitrarily small, can't you?
Exactly. You can set k here to be, for example, times 1 over delta here.
Mm-hmm.
And this would be maybe like, yeah. Then this would be delta instead. But you can see that the number of copies here is proportional to 1 over delta. But the next trick gives you the copy of log of 1 over delta. So the idea is, whenever you are in the situation when you can apply Chernoff bound, we try to use it. Here we are in a situation where we can only use Chebyshev. So okay, just try to use Chebyshev until you get some constant probability, and after that you can apply Chernoff. So we use that, and it's gonna be better. Good question, very good question. Okay. So the idea is, let's say that I have like t many copies, right? And I here just count the number of count the copies that yi is too big, I is tiny, count the copies that yi is too small. Okay. So let's try to prove this together. Can you tell me what is expectation of I huge? So we can define this thing, like call it EI, to be even that I is too big, right? Then I would have that, so I huge EI indicate this event. So I huge is just sum of EI. Okay. So by linearity of expectation, EI, you have this. Okay. What is this thing? What is the probability that yi is more than this?
Can't we use a Chernoff bound now because yi is the sum of independent indicator variables?
Right now, we could use it, but right now I just said that yi, each of the y is just epsilon 1/2 estimator, so we're just gonna use that for now. So if I just assume this, yi is so yi is epsilon 1/2 estimator. So if we use this, how much this would be?
Is it a sixth or a third?
Well, it's just gonna be like at most 1/3.
At most 1/3.
Yeah.
But up top, you use absolute value
Right.
for both sides.
Right.
So if we're only looking, but here we're only looking at one side, right?
Right.
Here.
Right.
So-
So we cannot say that like we have the bound for both sides.
Yeah.
Now we just ask about the event on one side, but we don't know maybe we don't know that they're gonna deviate with half and half
Oh, okay.
probability.
I see.
Yeah. So we can just only use 1/3 bound here.
Okay.
Okay. So each of these is 1/3
Yeah.
at most. And we sum over t many guys. So this is at most t over 3. Okay. And the same reasoning, you have that for the same reasoning, you have that I tiny expectation of the tiny guys is at most t over 3. Okay. So now, okay. Now you have this. Okay. Now, if z deviate from q by more than epsilon q, then you know that I huge must be at least more than half, or I tiny is more than half of t. Right? Because z is like a median of all the y. If the median is actually like outside the range that we want, so more than half of the y are outside the range of these two. Like if the median is too big, if the median is huge, then it means that half of the yi's are huge. If the median is tiny, then half of the yi are tiny. So either like I huge is more than half, or I tiny is more than half of t. Right? So we expect that like each I huge and I tiny is at most t over 3. But if we are wrong, then this is like a deviate from t over 3 by quite a lot, by some constant factor. So and now we can use Chernoff bound. Okay, so we're just gonna use, okay. So if this thing is the case, then I huge and I tiny is big. Now we can use Chernoff bound. I'm gonna use a variant of Chernoff bound where like when x is a sum of random variables, where like expectation of x is at most mu, instead of expectation of x is exactly mu. Right? In previous class we used this form, right?
Yeah.
But here I just say that okay, expectation of x is at most mu. Then we have that x is more than 1 plus epsilon mu with this probability. So they are exactly the same, except that instead of having mu to be exactly expectation of x, mu is just a upper bound of x.
Yeah.
Okay. Well, I will not prove this right now, but actually you can try to prove this. If we have time, we're gonna prove this in class. But intuitively, it's super clear. Like even when expectation of x is mu, you have this much. So now x is even smaller than mu. So the probability that it's greater than mu by this factor, we get the same bound.
Yeah.
Okay. Okay, now so mu here is t/3. We ask what is the probability that x here is like at least t half. Well, this is just the same thing as saying that it's deviate from mu by like 1 plus 1/2 times mu, because mu is this thing and this is 3/2. So this time this is t/2. So just use Chernoff bound. We get this one. But mu here is like something like what? Like some constant times log of 1/delta. Big constant that is big enough to cancel all of these small constants, and you get basically e to the log of 1/delta. So this is just like delta, and I put delta/2 just to be safe, because I can do the same on the other side for I tiny. And then by union bound, we get that the probability that I huge is big or I tiny is big is at most delta, just by union bound, the two cases. Okay. So, yeah. So we get that this thing happen with probability at most I huge is large or I tiny is large. But each of these happen with probability delta/2, which is at most delta. Okay. So that's it. Like, this is the idea. Given any unbiased estimator X, just make like a KT independent copies where K is something like of this form, like some variance over expectation square. T is something like log of 1/delta. Take the average on each of this group and then take the median, and then you're done. Okay. So this is like a trick that is so generic and you can use in basically every place. Okay. But so note that like this trick we need this to be small, yeah. But many times for many times the variance is actually small compared to expectation. For example, when let's say that x is 0, 1, for example, or let's say x is between, if x is between 0, 1, then you know that the variance of x is at most expectation of x. Why is that? This is because variance is just this thing square minus this thing, right? But if x is between 0 and 1, then x squared is at most x. And this is something like a positive. You subtract something positive, so I can just ignore this. So variance of x is at most expectation of x when x is between 0 and 1. So like this is something that happens quite often. Variance is at most expectation of x many times. So when this is the case, just make a bunch of copies, take median, take mean, and then take median. You're good. Okay. All right. But 1 second. If x is between 0, 1, then I could just use, can I just use Chernoff bound? Oh, but when I use Chernoff bound, I'm just gonna get this exactly. Sorry. So what I mean is like, if x is between 0 and 1, then I could just take the average, I think, and I would be done. Yeah. I don't need median. Anyway, we're gonna see the application of this trick today. Yeah. Okay. So we're gonna look at the streaming model again. Okay. Just recall the setting of the streaming model, right? This is a case when you have your algorithm and the element coming to you one by one, and you have small space, right? And let's say each element in the stream is from bounded universe U. U is some number, some big number. And now we're gonna consider this frequency vector. Okay. So think like this is a vector in like a c to the u. That is, think of xe as a frequency of element e. Like if a number 1 is given to you, then like x1 would increment by 1. If a number 1 come again, then x1 increment to 2, and so on. So each of the xi count how many times the ith element occur in the stream. This is just frequency of elements. Is this clear? What is frequency vector? Okay. And yeah. But in general, like I can think like this too. Like we can imagine that is at okay. In general, you can think like this too, that like the update to the stream actually is of this form, where like just indicate the element and indicate how much frequency it should change. Like I give E and delta, and then XE should be updated by delta. Okay. So the example of scenario is like if the IP address E occur in the stream, then you count XE increment by 1. This is like a normal scenario when you just count the frequency of elements. But when I model the problem like this, where I just look at the frequency vector, I could imagine the case when like the update is actually XE equals like is said to be XE minus 1. That is, imagine that like this is like a deletion of the occurrence of element E in the stream. Okay. So basically my point is when I allow to update in this way, update the stream in this way, it's just more general. Yeah. It's not just like a sub element come and I count like increase XE by 1. Now I allow you to update XE in any way for each E. Okay. Can be positive, can be negative. Okay. And the possible question that we can ask is like, okay, like distinct elements, the thing that we have done. For distinct element is just to count the number of non-zero entry in X. But we can ask, like actually like in the streaming literature, we ask a lot of things on X. For example, we can ask, what is the norm of X? Or what's like what's the element e such that x is big compared to everything else. This would correspond to like some heavy hitters or some attack from some IP address, right? If xe, this IP address, is so big compared to everything else, it seems like there is an attack in the stream. So you can ask anything about x, but today we're gonna look at this question. Yeah. What about, can we estimate the norm of x? Okay. Which is kind of to this is true norm of x, which is what? Which is exe squared. So the true norm of x also kind of basically it's big if, let's say this is like xe, x which is x1 up to xu, right? And the norm would be big if there is some, some guy that is really big. Yeah. Yeah, it's some basic information about x. Okay. And what we want to do today is to get like a good estimator of the norm of x. Okay. In particular, what I want to get is this one. Just epsilon delta estimator of z. And then let's say I take the square of the whole thing. So I want that my z square is basically close to norm of x squared with high probability. With probability at least 1 over delta. Well, the trivial solution is to store the whole x, and that takes u numbers because, that's the size of the universe, but we're gonna see that we can take just like this many numbers, like 1 over epsilon squared times log of 1 over delta. Okay. And the algorithm is super simple. Here is the algorithm. It's called Tug-of-war. So what you do is like you start your estimator with 0 before any stream comes to you. And now let's say that h, that map, this should be u, map the universe to 1 and minus 1. And I want h to be four-wise independent. Can you tell me what this means? Do you remember?
Four-wise independent?
Yeah.
It means that like if you have 4 elements, the hash function that maps 4 elements to 4 different elements. I don't know how to say that without writing it out. Sorry, like x of a, b, c, d, or h of a, b, c, d is equal to I, j, k, l respectively would be 1 over m to the 4.
To the 4.
Yeah.
Yeah. Right. Good. Thank you. So the probability that like for all I 1 up to 4, h map the element I to like a number, I don't know, AI. Yeah. This is gonna be at most m to the 4. In this case, m is 2. So 2 to the 4, and this is just 1 minus 1. Okay. I would not like tell you how to get this. Actually, we see how to get this when it's two-wise independent before. like in previous class when like the way to construct is like based on some random matrix. Okay. And okay, this is my 1 minus 1, but you can think of this as a range from 0 to 1, 0 and 1, and the construction in previous class would give this one, but it's just 2 y's independent. Here we want 4 y's independent, and there is a way to get the way to make it 4 y's. That might be in a homework. Yeah. Okay. So okay. So this is in the beginning. We just start with z equals 0, and you like prepare some hash function that is 4 y's independent. And now here's a simple way to maintain z. Whenever I want to update, like the element I comes to you, and the frequency is changed by delta, then I just change z by delta times hi. Okay. For example, if hi maps to 1, then I just increase z by delta. If hi map I to -1, then I would decrease z by delta. Okay, that's it. And you can think like this. Yeah, n should be u. So z is just like a sum of h. Like you can think like z is really just a sum of hi times xi, where xi is the frequency of I. Right? You can see this, right? If I keep updating like this, then z is just sum over all I hi times xi. Question about this? Okay. And yeah, at the end we return z squared, and that's it. So it's super simple, but like it's not so clear why it's good. But let's try to analyze it. But anyway, like this is the reason why it's called tug-of-war is like it's kind of clear. Like it's like some element, like each element will be mapped to like either positive side or negative side, and then like you kind of the positive guy pull z on the positive side, the negative guy pull z on the negative side, and yeah, that's why it's called tug-of-war. And at the end you return z squared. Okay. Okay, but you see this is just like really simple thing that just you maintain one number. Okay, let's analyze this. Okay. So what I'm gonna do is like let's say I write down g. So every n should be u. Yeah. Okay. I write g to be like 1 minus 1 to the u, where like a gi is just like how I map hi. Like gi is hi. So you can see that z is just like a sum of xi times gi. And at the first glance, z actually looks useless, because you see, I claim that the expectation of z is just always 0. Why? Well, just expectation of z is the expectation of sum of I xi times gi. By linearity of expectation, you get the expectation inside this. But expectation of GI is just always 0, right? Each element GI is like -1 or 1 with the same probability, so expectation is 0. So each term here is just 0. Sum of 0 is 0. Okay, so you expect to see 0 from Z, so it looks like really useless. Okay, but it's not really the case for Z square. Z square is something useful, it turns out. It turns out that like the expectation of Z square is actually gonna be the norm square. Okay, so let's try to compute this together. So we have that Z square, just by definition, is a sum of xi, everything square. Okay. And now I can just write down this whole thing square, right? Like there's gonna be, okay, maybe I can just say, I just do this. This thing, xi is the same thing of this thing, j, xj, gj. I just multiply two things twice, so it's square.
Yep.
And now we're just gonna multiply this. Every term in the sum here need to be multiplied together. That's gonna be the term when I and j are the same, and it will give you this one. And when I and j are not the same, it gives you this one. All right. Now, by expectation, because expectation is linear, you put expectation inside. Okay. What is gi square? Always 1.
Yeah.
Because g is either 1 or -1. gi square is always 1, so you get this term. What about this? gi and gi times gj. gi and gj, like h is 4 wise independent. In particular, it's 2 wise independent. So you can put the like expectation of this product is product of expectation, because this is 2 wise independent. But each of this term, expectation of gi, you know that is 0. Expectation of gj is 0. So this term is just removed.
Yeah.
So you get basically this is a sum of xi square, which is a norm square. Okay. So we have C now basically Z square in expectation is norm square. So C square then is the unbiased estimator of the norm square. But what we want is to get epsilon delta estimator of the norm square. So what do? We just use the trick that we just learned. This is the generic trick. So make copies of tug-of-war sketch. Make a bunch of copies and then take average of each of the group and take median. Okay. I just repeat. C square is unbiased estimator of the norm square. We want the epsilon delta estimator of norm square. So just take median of means. Okay. Just take like a kt many copies like before, and k is this much, t is this much. Okay. And when we query, like when we want to know like the norm square, we just return them average of median of the average, and we are done. Okay. Like you just take a bunch of copies here, take the median of the average. That's it. Now, okay, how many copies do we need? We need t time, like k times t many copies. This one is like of order log of 1 over delta. That's good. But we need to say that k is actually small. We need to analyze this one. That this should be constant. If this is a constant, then the total number of copies is just like is what we want. Okay. So I claim that this term is just at most 2.
What does it mean to make independent copies of z in this case? Would that be like you use a different hash function for each?
Yeah, you need to use different hash function. Yeah. So each of the hash function will take some small space because it's just 4-wise independent. And then you make like kt many copies, independent copies of the hash function. Okay. Okay. So ignore this thing. Sorry. If this is small, then you get that we need how many, like the space that we use is just log this square times this much number, like number of z that we maintain, and basically 4-wise independent hash function. This you're gonna need like a constant number, like constant space too. Yeah. Or like you can think like it's gonna be something like log u bits. Yeah, O of log u bits. You're gonna see how to construct this, yeah, later in the homework. Okay. But anyway, we need to analyze this one. That k here is actually just order of like just kind of order of epsilon square, 1 over epsilon square. Okay, let's try to do that. Well, it's now really about calculation. Okay, and let's try to do it. Okay. We want to analyze this one. And recall that the variance of z squared is just this. Okay. Maybe I let you spend like 3 or 4 minutes to try to work with this. Like, just try to prove this. So C is a sum of xi/gi. Variance of C is expectation of variance of C squared. Is expectation of C minus expectation of c square. Okay. Let's analyze. First. Yeah, I encourage you to try to calculate it yourself because just to get used to this kind of calculation sometimes is helpful actually. Okay, maybe let's try to do it together. So the variance of c squared is just like an expectation of c to the fourth minus expectation of c squared, the whole thing squared. Now just need to analyze each term. Let's analyze the first term first. Well, it's like this thing to the fourth. Just like expand everything, you get this whole thing. Because expectation is linear, just put the expectation inside. Now, okay, it's just okay how to analyze this one, right? Well, first of all, there are many cases here, but suppose I say that suppose that I is not equals to if I, J, K, L are the same, for example, then this would be like a G to the I square, G I to the fourth. Okay, and but okay, suppose that I is not equal to j, k, or l. Suppose that I is just some unique index among the 4 indices, right? Then this would equals to gi expectation of gj, gk, gl. Why can I do this?
It's independent of.
Because they are independent, but like it's 4y is independent.
Yeah.
2y is not enough, but it's 4y, so I can do this. But then what would this be? 0. Okay. So because this is 0. So if there exists one unique index among the 4, then this is 0. Okay. So the only case that this whole thing is not 0 is just two cases when like 4 indices are all the same, or actually you have like a pair of 2 guys. So I can say that the 2 cases when all indices are the same. So you get xi to the 4th and expectation of gi to the 4th. And then next is when you get like 2 pairs. There are like 4 choose too many ways to pair them. Okay. And right, 4 choose 2 many ways to pair them up. And then this would be I not j, and this is x square expectation of g I square gj square. Make sense? I need this term, right?
Yeah.
What is this? It's just 1.
Yeah.
Okay. All right. So now yeah, I just write down plus 6, right? Okay, so let's follow. It's up to here now. It's up to here. All right. So now I'm gonna like we're gonna do some trick. Okay. So I'm just gonna do this trick where like this term is just gonna be
I see.
like yeah. Let me just explain this. Like because you know that the sum of ai square, just like before, you have like a square term and cross term here. Then the sum of x I square, everything square, is sum of xi to the 4th plus cross term. Okay. So this thing is just this thing. Okay. So now, so it means that this thing times 6 is just 3 times this one. Right? Like this thing is just this minus this. Okay. So so now like I have this one, and this would cancel with this one because it's something that is this term minus this term, which is like 3 times this term, and this is like a, so it's some, like I can cancel this with this. Yeah. So I get this 3 times this one. This is just a norm. This is norm to the 4th. So this should be 3 times norm to the 4th. Okay. All right. So at the end, now I get that this one is at most 3 times norm of x to the 4th. Okay. Did I analyze this already? What is expectation of c?
Squared.
C squared? I reanalyzed this already. This is just like a norm square. Okay. So now what we want to analyze is then variant of z squared over expectation of c square. So okay, this is then at most this minus this, 3 norm minus norm square to the 4th because I squared it here, and this is 4th. This is at most 2. Okay. So yeah. So, but yeah, you see that like this is a place where we need the fact that we can factor this thing out or factor this thing out, we need 4 y's independent. Less than that, it doesn't work. Okay. So that's it. Like again, the algorithm is just tug-of-war. Like every element just random to positive or negative. Like, and you return the sum of the sum of like the sum of everything square. Any questions? Right. So basically, this is like, I hope that like at least in the past few weeks, you see like some really remarkable power of randomization. For many problems that it's just seem hopeless for deterministic algorithm, like to do it in sublinear space, sublinear time, we can do all of this with really simple algorithm by using hash function or some randomization. Right. So the next part of the course after the break, we will see another like a way to think how to approach many computational problems, basically using linear program. How many of you have learned linear program before? Okay, like you too. Okay, right. We will try to at least not just use linear program as some black box to solve some problem, but actually use it as a way of thinking. And to look at linear program, you will start with MaxFlow. MaxFlow is like a kind of a problem that is concrete enough, and it's like a special version of linear program. It's gonna be graph algorithm that people still look at it today, and like actually one of the main research area, like research topic that I am working on. I try to develop like a fast algorithm for MaxFlow, and it's this MaxFlow already, like you can use it to solve like 20 other problems, and once you go to linear program, it's like 1,000 of problems. Okay, so that's the next part of the course.